This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Welcome to the fourth tutorial of the William and Elsa Heraeus International Winter School on Gravity and Light. Today's topic are differentiable manifolds. We start with 15 statements. A. The function f that goes from R to R, defined by f of x equals x squared, lies in C3, where C3 means the function that lies in there is 3 times continuously differentiable. So we can do the first derivative, that's 2x, the second one is 2, the third one is 0, and all the others are 0 too, but all the derivatives are continuous, therefore this is true. Now the function f is defined by f of x equals absolute value of x, and we should judge whether this lies in C2 or not. But if we draw the function absolute value of x, we see that there is a kink, and surely here it's not differentiable. Therefore, the second one is incorrect. Third statement is the function f is now defined as the absolute value of x to the power of 3. And we have to judge whether this is in C3 or not. We need to draw this again. So that's the function. Clearly we can derive it once, and we arrive at this one. That's on the positive x-axis just 3 times x squared, and on the negative x-axis we have minus 3 times x squared. So this is the first derivative. The second one produces this one and this one, where this is 6x and this is minus 6x. And there's a kink, and therefore it lies not in C3. The fourth function that's given is the exponential function of the absolute value of x. And this statement says that this lies in C infinity, but when you draw this you see that at the 0 there's a kink again, and therefore it's false. The last one is the logarithm, the natural logarithm of x, but the domain is now restricted to R+. So the picture is this one, and if we restrict us to R+, this is of course infinitely often continuously differentiable. Therefore that's true. B. Which statements on differentiable manifolds are true? Every smooth manifold has a maximal atlas. That's true, because a manifold needs an atlas that covers the whole manifold, or the whole topological space, and then it's a manifold. And a smooth manifold just gives some statements on the transition functions, and any atlas can be made into a maximal atlas, and therefore every smooth manifold has a maximal atlas. Every C2 manifold is also a C1 manifold. That's true, because every function that's C2 is also C1. Every differentiable manifold is also a topological manifold. Of course, because differentiable means the manifold is Ck, let's say, k greater or equal than 1, and topological means that it's C0, and that's true. Now comes a tricky one. In C infinity manifolds, chart maps are differentiable. In order to say this, we need to think about it, and here's more space, therefore we draw a picture. Now we recall that a function that goes from some domain U, some subset of the manifold, into Rd. This function f is called differentiable if the chart representative of this map f here, I wanted to say the function f goes into Rd, and now some chart map, let's say x tilde, goes into Rd2 because that's a d-dimensional manifold, and f is called differentiable if this map here, so f after x tilde inverse, is differentiable. Then we call f differentiable. So now we have a special case, and the special case is we pick f equals x the chart map that we want to look at, this chart map. And as well we pick x tilde equals x, because we can take any chart we like because we have a smooth atlas. And if we now consider this expression with the special cases in there, that's x after x inverse, which is of course the identity on Rd, that is clearly differentiable. Therefore, in a C infinity manifold, chart maps are differentiable. The definition of a CK curve on a manifold, one should say, requires a C m larger than k manifold. That's true because we need the atlas to be at least CK when we want to judge the CK differentiability of a curve. Therefore, this is true as well. C. A differentiable manifold is always a topological space. That's true since by adding the atlas we of course keep the topological space, so it stays a topological space, but gets more structure by becoming a manifold. The second one is a differentiable manifold has enough structure to constitute a vector space. Of course not. A differentiable manifold is a generalization of a set. No, it's not. It's a specification of a set, but not a generalization. A differentiable manifold requires the discrete topology. No, it doesn't. It can carry any topology that it likes. A differentiable manifold features at least one set of charts that cover the whole manifold, or that covers the whole manifold. And that's true because that's the idea of an atlas. Every atlas has to cover the whole manifold. So C, the last one of C is true. And we move to the next exercise. We continue with exercise 2, and now the topic is the atlas and the way from topological to differentiable manifolds. We start with a topological space, R, equipped with the standard topology, and we further have an atlas, A, containing two charts. Each of the charts cover the whole manifold, but they can of course be together in an atlas. The chart maps are given by the map X, which is the identity map, and the map Y that maps some element A of R to A to the power of 3. And we should now construct the transition map, the chart transition map Y after X inverse, and give the differentiability class. So the picture here would be the following. Let's say this is R. It's just a set, so I can draw the circle or whatever I like. And we have two chart maps. First one is X, second one is Y, and these now map to the real line R. And between these two chart targets we have the chart transition map Y after X inverse. And that's the thing that should be calculated. So Y after X inverse takes some element A that comes from R, and we can simply calculate this. That's y of x inverse, but x inverse is the same as x because it's the identity, therefore here's just an a, and y maps this to a to the power of 3. And of course a to the power of 3 is c infinity of r to r, so this is a smooth chart transition map in the one direction. Now we consider the other direction. So we are constructing x after y inverse, plug in some a that lies in R. This is now given as x of y inverse is the third root of a. And the map x does nothing, so that's what remains. We may draw this in order to judge the differentiability class, and the picture is the following. So here we have infinite, well, the tangent is parallel to the y-axis, and of course if we do the first derivative, then we have a pole in here. Therefore this function is not even c1, it's c0, that means continuous on R. And what we see now is R equipped with the standard topology, and this atlas, as it is given up here, this one, is not a differentiable manifold. So here, no. But, and this was mentioned in the lecture, that by restricting an atlas of a topological manifold, which this was or is, we can make it into a differentiable manifold. So the question is, what do we have to do in order to make R O standard with the atlas A into a smooth manifold? And the answer is simple. We just remove one of the charts. Remove one of the charts. And it really does not matter which one, because if we remove one, only one is left. It stays an atlas because it covers the whole manifold, and since there are no chart transition maps, of course this is smooth. Therefore we made R equipped with O standard, and this new atlas, we made it into a differentiable or even smooth manifold. That's it for this exercise. Let's continue with the third exercise. That is an exercise on soft squares on R cross R. So we have a set R cross R, or R2, equipped with a soft square topology and an atlas A containing charts UN, XN. And these UN are given by the soft squares that also define the soft square topology. That means all tuples in R cross R where the absolute value of each of the entries is smaller than some n, and here we just consider n from n plus. Therefore just positive integer numbers. So to draw a picture, this may look like this is U1, there's one, this is U2, and so on. Okay, and the chart map is given here. So in the first entry we sum x and y divided by 2n, and in the second entry the same thing but with the difference of these two. First exercise is to recall the definition of a chart and show that UN, XN are indeed charts. So the first thing we need to check here is UN an element of the topology, and that's clearly the case, because that's just the way the soft squares are defined. Second thing we need to show is that the chart maps are homeomorphisms. That means the xn that go from un to x of un, xn of un, part of R2, these need to be homeomorphisms, which means they are invertible and in both directions continuous. So we consider the direction un to xn of un. This is clearly continuous because we have the standard topology and, well, I think that's clear. The other direction, we need to calculate the inverse that goes from xn of un into un. So it picks tuples and they are mapped to, now we need to calculate the inverse functions, and I did this already, and this is n times a plus b and n times a minus b. And these are, of course, continuous. Therefore, un, xn are charts. Second question is, we should show that A is a CK atlas by explicitly constructing the chart transition map, or the chart transition maps between any charts, and then state what K is. So a chart transition map is some xm that belongs to the chart umxm after another chart map. I'll draw the picture in a minute, and we need to have this from xn of un, intersected with and this goes to xm of un intersected with And here's the picture. We have, here's the manifold. We have that's xn. We have the chart map xn and the chart map xm. And this is the chart transition map. Here's R2 and there's R2 as well. Okay, so in order to construct this map, we feed it with a tuple AB and just plug these in here and calculate the result. So this is xm of xn inverse. We calculated here, therefore this is just n times a plus b and n times a minus b. And the other direction was given up here, so need to plug this in and arrive at, now this is m over n, that's wrong, so it's n over m, and here we have x plus y, but a plus b plus a minus b is just a, and here the coefficient is the same and b remains. Therefore we can write this shorter as n over m times ab. So we see the chart transition map, and notice we have both directions in here since we did not specify m and n. Therefore that's the most general chart transition map that's possible here, and therefore we see that this is of course smooth because it's just the identity map, maps AB to AB with some factor, but this does not matter and does not infect the differentiability. Therefore we can conclude that K is infinity. We have a smooth manifold. The last thing to do here is the third question, and it says construct at least one other chart that would lie in the maximal extension of A and prove that it does. So by maximal extension we mean we can add as many charts as are compatible to the other charts, and by compatible we mean C infinity compatibility. That means the chart transition functions have to be C infinity. And we think of an example, that's really just an example, you can pick any other one, call it x tilde, that's the chart map, and the chart domain is, say, U5. Does not really matter, but I picked U5, and this goes to x tilde of U5, which is clearly a subset of R, not D, but R2. Okay, and now I have to tell you what the map does. It takes tuples from the manifold and maps them to, well, just itself. Pick the identity map. But that's clearly another chart, and what needs to be checked now is whether the transition functions to any other chart or from any other chart to this one are smooth. And we can write them down. This is in the first place x tilde after xn inverse, and this one takes some a and b, and this is mapped to a plus b over 2n, a minus b over 2n. Maybe you need to construct this, but that's the right result, and this is of course smooth. And the other direction, which is xn without the inverse gets here, goes here, and we again plug in some a and b, and this is a plus b. Sorry, the inverse was missing. Oh, I did this the wrong way around. I'm really sorry. I need to correct this. So this has to go and this has to go, because here we have the inverse of the chart maps that we defined above. That means this is n times a plus b, and here n times a minus b. And now here we get this a plus b over 2n, and here a minus b over 2n. And this is again smooth, therefore we added a chart to the atlas that of course would lie in the maximal extension of the atlas. That's it for the third exercise. We continue with a very short exercise 4, but it's important because we introduce a good notation for partial differentiation. We have a map F that goes from Rd to R and denoted as del sub I on F is the partial derivative with respect to the ith entry. But the important point here is this object, so the derivative of F with respect to this entry is again a map in its own right, and again a map from Rd to R. To see this, we are given a function f from R3 to R3, and it looks like this. And we have to calculate some derivatives. To calculate the second derivative of f is, that means we derive in this special case with respect to beta. That means this is 2 alpha to the power of 3 times beta plus 2 beta delta plus 0. But as I said, this is a function in its own right and it's evaluated at x, y, z. Therefore the result is 2 times x to the power of 3 times y plus 2yz. We do the same thing here, calculate the derivative with respect to the first entry, and this produces 3 alpha squared beta squared, but evaluated at square circ star, therefore we have 3 square squared times circ squared. So really we first take the derivative and then we evaluate at some place. Now we take 2 derivatives after each other. Why not? So the first one, del 2 on f. We had this before, so this was 2 alpha to the power of 3 times beta plus 2 beta delta. And now we derive again with respect to the first entry now, which was alpha here. Therefore what remains is 6 alpha squared times beta, but we evaluate at ABC, therefore the result is 6a squared b. And here we perform 2 derivatives of the third entry, which is delta. So the first, which is delta up here, so the first derivative yields beta squared plus 1, and we derive again with respect to delta, that's 0, and therefore the result is 0, but not because we plugged in the numbers first and then derived some constants which yield 0, but it's 0 because the second derivative itself was the 0 function. So that's it for partial differentiation, and we will apply this in exercise 5. Last exercise for today, for this tutorial, and it's exercise 5 on differentiability on a manifold. The subtitle is how to deal with functions and curves in a chart, and we will draw diagrams here, or one big diagram, and this is a really important thing because visualizing these maps always helps. We start with the smooth manifold MOA, that is d-dimensional, and we have a chart UX from the atlas A together with a smooth curve that goes from R to the chart domain, and a smooth function that goes from the chart domain to R. The first question asks us to draw a commutative diagram containing the chart domain, chart map, function, curve, and the respective representatives of the function and the curve in the chart. So we start, as we always start, with the manifold M. We have a subset of this manifold that's called U. On this manifold we have a curve gamma which takes real numbers and maps it to the manifold. Could draw something like this, and that's the curve gamma, but we don't have to. We also have the function f that goes from the subset U into the reals. We've also given a chart X, this one up here, that of course goes to some subset of RD. So we drew chart domain, chart map, function and curve. What's missing are the representatives of function and curve in the chart. So we want to talk about the curve gamma in the chart, and that's this one. So everything that's been in the manifold before is now pushed down into the chart by the chart map X. And this arrow is X after gamma. Therefore X after gamma is the chart representative of the curve gamma. And similarly we have the chart representative of the function f, and that's f after x inverse. So we go up the other direction of x and with the function f. These are the two chart representatives of function and curve. And again, to emphasize that, that's an important technique in order to understand these things. Next question and that's the last one for today, asks us to calculate this object. So the function f after gamma derived some parameter lambda. The first question we should ask is, does this make sense? So deriving f after gamma. Therefore we have to look from where to where it maps. You can look at the diagram. So it first takes gamma, the values, the domain of gamma, which is R, is mapped to U, and after that we take the function and map it to R. Therefore, this one is a map from R to R, and therefore differentiation makes real sense. And to do this, we start here. F after gamma prime of lambda equals. We would like to use some chain rule because we have an outer function and an inner function, but the problem is these functions have target and domain in the manifold, and there we have no notion of differentiating. Therefore what we do is we use the chart representatives. So we go down in the chart by the chart representative of gamma and up to R again with the chart representative of f. Therefore f after x inverse after x after gamma. And you see this is a 1, therefore that's of course the same as this side. And since the composition of maps is associative, we can set brackets here. Okay. In order to make this a little simpler, we define this one as capital F and that one as capital gamma, just to keep notation simpler. And now we want to apply the chain rule, and the formula goes like this. So del I we derive with respect to the ith component, and we derive capital F evaluated at gamma of lambda. So that's the outer function, so to speak, evaluated at the inner function, and the chain rule tells us this should be taken times gamma, the ith component of gamma, derived at the point lambda. And since we know f and gamma, because this is just capital gamma and this is capital F, we can plug these in and calculate the result. Okay, so deriving f with respect to the first component yields 2x. We would have plugged in x and y, but we plug in the capital gamma, which is cosine sine. So we evaluate this derivative at cosine sine. That means we have 2 times cosine of lambda, but times the derivative of the capital gamma of the ith component, and we are, of course here it's summed over, we had this before, and therefore this is 1. Deriving the first entry here yields minus sine of lambda. That's the first summand, and the second one is similar. We have 2 times y, but evaluated at here. So we have sine of lambda times gamma 2 prime is cosine of lambda. And you see this minus sign cancels the second term, and therefore we have 0. Maybe you could think about this, because the curve gamma in the chart, so this capital gamma, describes a circle. So we have a circle where we run around all the time with the parameter lambda increasing, and the function that we look at when we run around is x squared plus y squared, but on the circle this is always 1. So the values of the function around the curve, along the curve are constant. Therefore, the derivative is 0. So that's it for today. See you next time.